Hello everyone, in this video I'd like to talk about the paper that proposes a method called mask autoregressive models, or MAR, that you can use it to generate high quality images like all these ones that you can see on the left. And all you need for it is just some autoregressive models, and you can use it to solve the problem in a continuous space. And yeah, I hope you enjoy it, and let's get started. Autoregressive models and natural language processing models behave this way: that we have a set of words like this to shall, and we are interested in predicting the next word, in this case pass. But for that to make happen, we need to define a vocabulary containing all the possible words that we can have to replace. Then, given all the information present in the this to shall sentence, our model should predict a d-dimensional vector, that is the embedding size of the model and is free to be anything, and then a classifier is trained to transform this predicted d-dimensional vector into a k-dimensional vector that has the same size as our defined vocabulary. But one issue is that the values in the estimated k-dimensional vector are logits, and they're free to be anything. So we just use the softmax just to turn these logits into probability values, and you can imagine that the derived vector to be something like this, that has small values for all the values except the entry 1097, that is for the word pass. So we can grab the entry 1097 from the vocabulary and place it as the predicted word. And the question that you can ask is, what if I want to have more diversity in next token prediction? Because currently it is only predicting the word pass given the sentence this to shall, which might not be ideal. And we might want something like this to shall end, or this to shall improve, or this to shall change. And for that to make happen, we can define a temperature value inside the softmax to control the diversity. And to show you how, let's just denote the predicted d-dimensional vector by z, the classifier by w, and the whole procedure as a conditional probability that given z, the predicted embedding by our model, we are interested to derive x, that is a k-dimensional vector, to specify which word to select. And for defining this conditional probability, when we include the temperature value, it can be defined this way, that is everything exactly like it used to be, but we divide the logits by a temperature hyperparameter before passing it to the softmax. And to show you how it changes the probability vector, let's just assume that logits we derive from our model is this. If I don't include the temperature hyperparameter and just take the softmax, this would be the derived vector that looks like a uniform distribution, and second value in the vector is the highest. So I can just simply grab the second element from the vocabulary and say that's the next word I predicted. However, if I want to add diversity, instead of using Rmax to always grab the second element in the array that is the highest, I can use GumbleMax that doesn't always select the highest number in vector and instead randomly selects one element from the vector, but the probability of selecting that element depends on the value it has. Like the second element is more likely to be selected since it has the highest probability, and then the first element has the least probability, so it is less likely to be selected. And that's where the temperature hyperparameter comes in. It says if you put a very small value like 0.05 as the temperature, the probability turns into this, that if I use GumbleMax, then 96% of the time we select the element 2, and we barely, like the remaining 4% of the time, we select the other ones. And if I put a large value for temperature like 10, then it turns into a more uniform distribution, so all of them become equally likely to be selected. But this is for the natural languages, and then we can turn into computer vision example, and we want to see how we can use the same autoregression but for the images instead. For images, we can split the images into patches and consider each as a token. So the job is, given a series of patches from the top left image, the neural network has to predict what is the next patch. But there's one particular issue with this. If I use 16 by 16 patch size, considering that we have 3 channels for each RGB pixel inside the patch, then we have 16 times 16 times 3 pixels inside the patch, and each pixel can take 256 different values, ranges from 0 to 255 for sure. So we have almost 200,000 of possible values that we can assign for a single patch. That is quite a lot. Also, a note from the feature B, an alternative perspective that we can also have is that we have infinite different values that we can assign for a color. But what we do is that we just split it into bins, like 256 different bins, and we only use that to assign a color. But in reality, we can have more spectrum of different values that we can assign for a color. And if we solve the problem in a continuous way, then we kind of account for that we don't really have it in a discrete space. And among all of these possible values, there are a lot of them that quite garbage. I can arrange them in any arbitrary order, but visually when we look at them, it doesn't have any special structure at all. So one possible idea is to limit the possible values, and the idea is just to define a codebook with a fixed size k, and you can consider it as a dictionary that the keys are just some indices and the values are some 16 by 16 patches that we are pretty sure that they have some special meaning and not something garbage out of nowhere. But how do we make sure these are meaningful? We can let the model learn it. And the idea of doing it is called VQVAE, which I'm not covering in this video. But the thing is that if I use VQVAE, it has some limitations that in the paper they are talking about. And the first thing is that the reconstruction of VQVAE is not as good as a model that works in a continuous space. The reason why is because when the model outputs a new token, we have to go and search in the codebook and pick the patch that is the most similar. I mean, they're not doing it in a pixel space and they're doing it in a latent space, but we can assume it in a pixel space and then just assume what I'm going to talk about. And assuming that we are selecting the most similar one, the most similar patch is not allowed to be anything out of all the possible patches that they are especially meaningful. I mean, I said there are 200,000 possible values, right? Let's just say, presumably, we have 5,000 of values that they're especially meaningful, but the codebook size that we are defined is 1,000. That means there are 4,000 of values that they're meaningful that we don't cover it in our codebook. And we have some quantization error when we want to match it with the most similar one. Hopefully it makes sense. And the second issue is that they are difficult to train and are sensitive to the gradient approximation strategies. So here the others come and they say, let's just do this autoregression in a continuous space instead. And there are two properties that we should consider. First thing is the loss function that we needed, otherwise we are clueless how to train the model. In discrete space like natural languages, it is easy. You just need to predict the output probability vector qx among k possible values and assign a one-hot vector px that is 1 for the index of, let's just say, the word that is the ground truth and 0 otherwise, and we minimize it using cross entropy. But the other thing is a sampler that at inference time we also care about variety and we don't want to always output the same thing. And in discrete space, as I said, we control it by varying the temperature value inside the softmax, and then we use Gumbel max instead of argmax. But how can we do it in continuous space? That's where this paper begins. They propose this thing that we predict next token, and instead of discretizing it in methods like VQVAE, we use something else, which is diffusion loss. And in diffusion, it's just an MLP that receives noisy xt as the input to be denoised, and in our case this xt could be the patch that we have, but in a noisy version of it, and it is conditioned on a vector z, that it is a context vector that has to encode whatever information it has seen from the previous patches. And then the model conditioned on this z predicts the epsilon value that is the noise. So you can kind of consider this diffusion as a model that has to predict the conditional probability px given z, meaning that when the model output a vector condition z, it should be considered as a contextual vector that encodes whatever information we have seen in the past, which are just some image patches in our example, and we use the diffusion as a form of score matching that pushes us towards a distribution of patches that are having high scores given the condition z that we have. And just to show you visually what I mean, let's just look at this image that I borrowed from Dr. Sung's blog post. In this image, as you can see on the left, we have data samples, which are two distribution of images, one on the top right, the other on the bottom left, and everything else in the middle can be considered as some sort of noise images. And then we can define a score function that is gradient of log of probability distribution. If you want to know why the score means that, check out the video I put on the description that Dr. Song explains why, but intuitively it should be some directions towards the distribution, which is the exact opposite of the noise that our denoiser in the diffusion model predicts. And assuming all these areas are pure noise images, let's just sample one random Gaussian noise. That should be a point like this one, right? And then what we try to do is just to remove the noise using our denoiser. And removing the noise from our denoiser should be equivalent of adding this score function result, which is just some errors towards the distribution that we learned in the training. So one step denoising pushes us one step towards the distribution, and doing it again pushes us one step more, and we can do it again and again until we reach the distribution of the images we have. But in our case, we also have a condition z. So that means instead of pointing to a nearest distribution of images in the space, it goes to a distribution of patches now that aligns with the contextual vector z that we have. And hopefully we're all on the same page. And now let's just see how we can model the two properties I mentioned before. The first one was loss function, right? And for this loss function, you can check that out in the video I already made explaining how diffusion models work. And as a quick reminder, we can create xt by starting from our patch image x, and then we can define a neural network epsilon theta that is our MLP in this example, which receives the condition z, and time step t, which should specify how much noisy the xt is, and generate a pure noise epsilon with zero mean and unit variance that we sampled from a Gaussian distribution. And then the loss function would be this expectation that we compare the output of our model epsilon theta with the ground truth epsilon to see whether it can predict the underlying noise or not and penalize it if it can't. But note that this expectation is over epsilon and also time step t. Usually in diffusion models, we just randomly select a time step in the middle and then we add noise to the image correspondingly using the first formula that we also see here. But here in this example, since we are dealing with MLP instead of the usual unit, we can do it multiple times and then take the expectation. And more specifically in the paper, they say we do this 4 times for each image and then we take the expectation just to improve the convergence. And that would be about the loss function and training. And the second thing is about the sampler, that we want to generate something diverse and not something the same all the time. And for defining the sampler, recall that backward process in the DTPM that we have this formula, and then the second term is the one that has to add stochasticity in the backward process. But then comes the question that can we use the temperature we had in discrete case here to control the diversity? And the answer is yes. And the way how is that, remember I told you in the video that the epsilon that the denoiser predicts is proportional to the negative of the gradient of the log probability, because gradient of log of probability are just some directions towards the data distribution, just remember the arrows, and the noise is exactly the opposite one that goes away from the data distribution. And having this in mind, we can insert the temperature to the conditional probability we have by using 1 over the temperature in the power of this probability. But we have the gradient of log of probability, so we can take the log and the power goes behind the log, and then take the gradient and we have this thing. And since the gradient of log of probability is proportional to the epsilon, but the difference is just the direction and also just some scale, which is, I haven't shown in the slide, but it is just the square root of 1 minus alpha, but that's not important. But the thing that is important is that since these two are just proportional, scaling the log of probability by temperature is equivalent of scaling the epsilon value by 1 over temperature, and that way we can control the diversity. But there's one paper they referred to, which is this paper called Diffusion Models Beat GANs on Image Synthesis from OpenAI, and in that paper showed that in practice we can scale the delta parameter by temperature value, and it has the same effect, and authors decided to do this instead. So instead of just dividing the epsilon value by temperature, we just divide the delta value in this second term by temperature, and those are exactly the same. And using the things that I just explained so far, it is enough just to model the autoregression in a continuous space. But the others go one step forward and they try to unify autoregressive models and mass generative models and show that mass generative models can be categorized as a subset of autoregressive models. And if you don't know what mass generative models are, I can show you this mask GIT as an example from CVPR 2022 that the training happens in two stages. In the first stage, which is called tokenization, we try to use VQVAE just to encode the image into discrete visual tokens and then train a decoder that tries to decode those discrete vectors in the latent space and reconstruct the original image. So the first phase is just some reconstruction task. And once we do it, we have the second stage of the training for the generation. And here we randomly mask some of the tokens in the image and train a transformer model to predict what are those missing patches are. And at inference time, we start by masking all the tokens and the transformer predicts some sort of patches. But instead of having them all, we keep only the small portion, like the 5% that the model is confident about them, and remask the remaining 95%. And we do it over and over iteratively, and then finally we generate some sort of images. And as you can guess, here in the generation part, they also use gumball max and temperature to control the diversity. And then just to show how these mass generative models can be considered as a subset of autoregressive models, we can first look at this thing, that the others say bidirectional attention used in mass generative models can also be used in autoregressive models as well. Because all we care in autoregressive models is just some next token prediction, right? But the thing is, what people usually use for doing it is causal attention instead of bidirectional attention, that they use mask attention in their method. And as you can see, we start by a start token S, and the first output only relies on context from this encoded token that only receives the information from the token as start token S. And then the next output token only receives context from these two encoded tokens, and generally each output only has information from the past. And ultimately we have this next token which the model predicts about the next step. But this paper says we don't really have a constraint to do the autoregression using causal attention, and instead we can use bidirectional attention that is very similar to mask autoencoder approach that I also have a video about it. You can check that out if you don't know how it works. But in a nutshell, we have an encoder that every token is connected to every other tokens, and then we generate some encoded tokens. And next we have a mask token M. We just concatenate it at the end, and then we have a decoder that receives as the input the output of the encoder in addition to mask token, which has to predict the missing value in the next token. So now you might see that autoregressive models are more similar to mass generative models, but there's a question that what's the difference between causal and bidirectional models in practice? The first difference is the advantage of bidirectional ones, that we are not limited to predict only next token, and we can concat multiple next tokens to predict like multiple mask tokens simultaneously, and the decoder can just predict them all together. So that just have some speed improvement in the generation. The other difference is that with bidirectional, we cannot use key value cache that we can have in causal ones. And if you don't know what KV cache is, just look at this kef that I took from a medium block. And as you can see in different steps, there are many repetitions, and the query, key, and value tokens from the previous tokens are computed exactly the same. I mean, like at the step 3, the key, query, and the values of token 1 and 2 is exactly the same as it used to be in step 1 and 2. And just to reduce the repetition, the thing that they proposed is KV caching, that the query at each step is only for the token of interest, and all the key and values from before are cached and retrieved, since they have the same values, right? And just by using this simple implementation trick, we can reduce the time and make it around like 5 times faster. But unfortunately, we cannot do the same for bidirectional ones, which makes them slower. But the thing is that we still can reduce the generation step by predicting multiple tokens simultaneously and speed up the inference and reduce the time gap between causal and bidirectional ones. And in general, bidirectional ones are having a better quality since they are using full attention instead of mask attention, and they offer a better speed accuracy trade-off. And the final thing to talk is that we can apply this autoregressive models in random order instead of a raster order that we usually do, and the next token only receives the information from the previous patches. And the thing that they propose is this random order, that we first permute all the patches in the image, and then we have the autoregressive model that has to predict the next token given the previous patches, which originally in the image is just some random patches scattered in different area of the image. So now it is more like a mass generative model, right? And finally, we have mask autoregression, that instead of predicting only next token, we can do it for multiple next tokens. But keep in mind that if I want to do AR or masked AR, I don't really know what is the next token, so I also need to have the positional embeddings so as to make sure that the thing that I'm predicting is at which position. And yeah, that's all about this paper. I'm not going to talk about it more, except that there is one final figure that, as you can see, MAR works better than the diffusion transformers and autoregressive models, that they are used cross entropy. They are having a better FID, but the thing is that the MAR can be used in different versions. This point, as you can see, has the best FID, but it is the slowest. And that's the case that if I want to use to predict only the next token. And this one has the best speed, but has the worst FID. And that's if I want to use multiple tokens. And the values in the middle are just if I want to use less tokens to be predicted as the next token. They are having the better quality, but the inference time is a bit worse. And yeah, that was all I wanted you to know about this paper. If you enjoy it, don't forget to like and subscribe. And until the next video, goodbye.